So we discussed that one way to find out how the energy or motion of a particle changes is to break its motion up into very small pieces, and in each piece you can see in what direction the force is going, and so you can see how that changes the velocity. Add up all those changes and you get the total motion. But certain kinds of force fields give us a shortcut where the energy change doesn't depend on which path you take. So if I went a different way to get from this point up here, let's call this point A, point B to make things clearer. Supposing instead of coming in on that path, I came in on a different path and I did this. I got there that way. Then I'd have different forces at each point along this line, and I'd have different length elements, and so I'd have to break that one up into different pieces. And when I add all those up, I might get a different value for the amount of work done by the force, and therefore I might get a different change in energy. But conservative forces have a special property. And that property is if you go around an entire loop, so if I went round from A all the way back to A again, my energy wouldn't change because my net work would be zero. So going from A to B on one path gives me exactly equal and opposite the amount of work of going back along any other path. And because if I change the direction of my path, all I'm going to do is change the sign because my force is going to be going in a different direction compared to my movement. That means I have to do the same amount of work no matter which path I take going from A to B. So going one way from A to B, I'll do a certain amount of work and change the energy by a certain amount. And if I go a completely different way, I'll also have exactly the same amount of work and change the energy by the same amount. And this is exactly why conservative forces like gravity allow us to talk about the concept of potential energy. And so we were able to talk about this roller coaster problem in terms of potential energy because the potential energy between this point and this point was the same no matter how we got there. And so we could work out the kinetic energy change by working out the change in the potential energy. And it's exactly the same for something passing by the Earth, and indeed it's exactly the same for any other conservative force. As an aside, that potential energy is actually enough to describe the entire force field. So if you know the potential energy for a conservative force, you actually know the whole force field. So we've been talking about conservative forces and potential energy in terms of gravitational fields because we're most familiar with them, but it's unsurprising because the electric field is almost exactly the same as the gravitational field, where you're exerting a force per unit charge instead of a force per unit mass. But it turns out, of course, that electric fields also generate conservative potentials. Remember that gravitational fields and electric fields aren't exactly in units of force, so they're not force fields quite. A gravitational field is a force per unit mass. So if I have a certain amount of mass and I roll it down a hill, it'll get an amount of potential energy proportional to that mass because it has a force that's proportional to that mass pulling it down that hill. And similarly, if I have a certain amount of charge, say in a circuit, and I have an electric field, it's going to experience a force that's proportional to its charge, and so it's going to get a certain amount of energy proportional to its charge. So if I have a hill, just a normal hill, I don't have a fixed amount of gravitational potential energy difference between the top and bottom of that hill, because if I put a kilo of mass down there, I'm going to get less energy than if I put a ton of mass down there. So what I really have is a certain amount of gravitational potential energy difference per unit mass, and that is called a gravitational potential. And that's not to be confused with the gravitational potential energy, because the gravitational potential energy is a property of the hill and a test mass, and it has different units because we have to divide by the mass. And the reason we do that is that the gravitational potential then is a property of the hill. If I know the hill, I know what gravitational potential I have. If I know I have a 200-meter hill on Earth, I know exactly how much energy I would get out of every possible test mass. And in exactly the same way, we define the electric potential to be the electrical potential energy of a test charge divided by that charge. So suppose you have an electrical device that you want to power. If you want to power it, you want to connect it to a battery. So schematically that looks like this. What a battery does is it provides a force on charges in order to push them around the circuit. So positive charges would go this way around. Actually, electrons are the things that move in circuits, but we can ignore that for a second. So it's pushing the charges around the circuit and it's giving them energy to do so. And what that battery does, it gives a certain amount of energy per unit of charge that it's pushing around. And so it has a fixed electrical potential. And you'll be very unsurprised to hear the SI unit that applies here. So if you have the SI unit for energy, that's a joule. And if you have the SI unit for charge, that's a coulomb. And 1 joule per coulomb is equal to 1 volt. So if you have a 12-volt battery that's running for 2 seconds with 3 amps running through it into the circuit, then those 3 amps for 2 seconds is going to be 6 coulombs of charge. And 6 coulombs of charge for a 12-volt battery is going to be 72 joules of energy that's delivered to that circuit. And that's why batteries are measured in volts.